Okay, you guys can see that already? Okay, everything looks good? Okay, so today the plan is to continue our discussion of scattering, but today we're going to move into discussing scattering with Green's functions. But before we do that, let's just sort of remember what we were talking about last time and finish that off. Last time we were talking about scattering off of a Yukawa potential. And there we had the potential looks like this. It's a screened potential, a screened Coulomb potential. And so we were asked, what is the differential cross section? And so then we found we used the Bourne approximation, which is that d sigma d omega theta. And so let's just remind ourselves of our scattering. There's our K initial, there's our K final, and this is theta. And so the differential cross section for some angle scattering into some angle theta is using the Bourne approximation. We just have to calculate the we just have to calculate the matrix element that couples the initial wave into the final scattered wave and square it like that. And so, but this, of course, is a Fourier transform that is kind of complicated integral, but we went over it last time. And if you do the complicated integral, then what we find is that we get this expression for d sigma d omega, the differential cross section scattering off the Yukawa potential. We get an actual answer for it, which is kind of nice. We can write it down in a simple form. And so when we write it down, it looks like this. And so, and then we have to square this. And so it's just this funny formula. But if you plot it, then it starts to make sense, because if we plotted it high energy, then it's kind of interesting. And when we say high energy, basically we're saying that this term dominates at high energy, because K squared is equal to, remember, 2me over h bar squared, right? So if I say big energy, I mean big K squared. And so high energy means that term is big. So it's basically saying that K squared R squared is bigger than 1. See over here. And so that's basically the same as saying that since, you know, K is a wave vector, then that's the same as saying that R over lambda is big. And so that's the definition of high energy. It means that there's a lot of wavelengths in the screening length. So you can fit a lot of wavelengths into the screening length. And so if you plot that, then it looks like this: d sigma d omega. If we just plot it, because it's 1 over sine squared theta over 2, then it's going to look like this. It's going to fall. That's at theta equals 0, and this is theta equals pi. And so we see that it doesn't, oops, I'm screwing this up. We see that it falls off. So it's peaked at theta equals 0. And so that means that basically this is telling us that if we have the K incident, then the highest probability is for the K final to be in the same direction, because then theta equals, because that's the situation for theta equals 0. And so it's like the potential it's like the potential is transparent. It's like it's not there. On the other hand, at low energy, then you can see from that formula that d sigma d omega is equal to a constant. And so if I plot d sigma d omega, then it looks like this, like that, from 0 to pi. And so that means that if that's my K incident, then I have equal probability to go in all directions. K final. So the probability is the same, because remember, d sigma d omega, we can think of it like the probability to scatter in a certain direction. And so then we can go one step further, and so this is then isotropic. We call that isotropic scattering. And so then we can go one step further, and we can calculate the total cross section by taking the d sigma d omega and integrating over what? Can someone tell me?
D omega.
Exactly, the solid angle. And so when we do that, then that's the same as, then that's basically integrating over solid angle. It's going to be we have sine theta, d theta, d phi, right? And so that's the solid angle, d omega, and then we have the differential cross section, which is going to be 2m v naught r squared over h bar squared times this 1 over 1 plus 4k squared r squared sine squared theta over 2 squared. And so you can do that integral. And when you do that integral, then you find that sigma total, the total cross section, and you get this simple answer, which is 2m v naught r squared over h bar squared, and then 4 pi over 1 plus 4k squared r squared. So there's a lot of algebra there. There's some algebra, but then you get these nice, neat answers. And so this is the total cross section for the Yukawa potential. And this total cross section is worth thinking about for a moment, because you can see that at high energy, because the total cross section you can think of as like the total probability to scatter. The probability to scatter, it's sort of like the probability to scatter in any direction. Now, cross section is not exactly a probability, because the units are wrong. It's an area, but it's an area that is proportional to the probability. So it's proportional to the probability to scatter into any direction. And so at high energy, then sigma total is equal to what? Somebody tell me. Just look at that formula. Can anybody see it? What happens to this formula at high energy? At high energy, yeah?
It's just equal to 4 pi.
Well, at high energy, this this k squared dominates.
Would it be the 4 pi times the value at the peak?
Well, there's no theta dependence here. It's just, if you look at this formula, then the k squared is at high energy, the k squared dominates, and so the whole factor goes to what?
Oh, it goes
Pi
to
over k.
pi. Yeah,
Well, it's k. Let's just say k goes to infinity.
yeah, like pi over k squared r squared.
Right. And what's that as k goes to infinity?
0.
Yes. That's exactly right. 0. And that makes sense because at high energy, it's like the potential is just a little tiny bump in the road. You know, you have a Mack truck zooming along, huge energy. It doesn't even feel that little bump in the road. But at low energy, then you have something different. At low energy, then you have that the cross section goes to this. And so this bottom part turns into 1. And so then you end up with sigma goes as 4 pi times this quantity squared, 2m v naught r squared over h bar squared. And this is kind of a cute thing to look at because it's sort of like that's equal to 4 pi r naught squared. And so it's sort of like the it's sort of like a it's sort of giving you the size of the scatterer. It's like saying that the waves are coming in and they're wrapping around that scatterer and zooming off. And so that, because that's sort of gives me basically the effective area of the scatterer. Okay, so this gives you a sense of how the Bourne approximation is pretty useful. The Bourne approximation is useful for many scatterers. But there are some cases, so I just wanted to give you that sense. So just taking basically just taking the Fourier transform of the potential, which is the Bourne approximation, gives you a lot of information about the scattering. All the scattering, a lot of scattering information is right there in the Fourier transform of that potential. But there are some cases where it fails. And so let's consider a case where it fails. So let's consider this situation. Let's take a hard ball scatterer. And so now we have this. It's like a billiard ball, hard ball scatterer that has some radius. I'll call it R naught. And then I shoot, and I'm shooting my particles at it, and I want to know what's the probability that they go off in some direction. So I have some K initial, I have some K final, and I want to know, and I'm asking you, what's the probability that the particle gets scattered into this angle, which is theta. And so I could say, what is d sigma d omega at theta? Same question I asked you before for the Yukawa. But now for the hardball scatterer, my potential looks like this. For R less than or equal to R naught, what do you think the potential is equal to for a hardball scatterer, a billiard ball?
Infinite?
Exactly. Right, because you can't get in. That's exactly right. But what happens if R is greater than R naught? What is it? Someone tell me. It's a hard ball. It's here, and if you're away from the ball, what is the potential? If you're not touching the ball.
0.
Yeah, exactly. Exactly. It's just like the heart. Exactly. It's like particle in a box, but in reverse. That's right. So that's the hardball scatterer. And so now you say, okay, you know that d sigma d omega from the Bourne approximation is proportional to that, that Fourier transform squared, right? And so then you say, okay, now I got to find that Fourier transform like I did before. And so let's find VFI. That's going to be the integral over all space of the final state e to the minus I k final dot r. That's the final wave. And I got it to integrate it over the potential times the initial wave. d cubed r, right? So that's what we got to find, just like we did for the Yukawa potential. But now I just want you to notice something. When I start integrating this over all space, what is this potential going to do? It's going to be 0 far away, but what's going to be close by? What's going to happen when I do this integral over all space? Because I got to integrate over all the space that contains the potential. So what happens when I integrate over this potential? What do I get? Somebody tell me.
Is it like pi r naught squared or something else?
Well, here's the thing. It's like I got to integrate. I got this, I got this ball. I got this wave. And that wave is, if I did it just like the Yukawa, that direction is z. And so that is the k final minus k initial direction. I picked that to be z, right? And so that means I have this wave, this plane wave. And I'm integrating it over all space. And all space here is the potential right there. And so when I'm integrating that, when I integrate over all space, when I'm integrating in this region inside of the potential, what is the potential equal to?
Infinity.
Yeah, it goes to infinity. So when I integrate over this region of the potential, which is infinity, what is my answer going to be? And it's a finite region. So I'm integrating infinity, not just over one point, but over a whole finite region. What's the answer going to be? If I have infinity, yeah, if I integrate infinity, I get infinity. That's right. Right, so it doesn't work, it diverges. And so this is clearly a situation where the Bourne approximation turns to garbage. It's giving you garbage. So it doesn't work. And that is basically just telling you that your approximations failed. And your approximation was that to get the Bourne approximation, you were basically saying I have a plane wave coming in, that's my initial state, and then I got a plane wave going out. That's my final state. And I'm just having sort of perturbation theory transitions from one state to the next. And so something is really going wrong with this approximation. And basically what's going wrong is that in this particular case, what's going wrong is that the plane wave is just a terrible approximation for what's happening, the wave function. So psi, for the Bourne approximation is basically saying that your wave function is a plane wave. But for this case, it's a terrible approximation. Sometimes a terrible approximation. And then it fails. Okay, so what do we do when it fails? Now, what do we do? So then what? What do we do? What happens? So what happens is we got to do something new. And we have to, let's reconsider scattering theory. And let's we have to do it, we have to approach it from a different perspective. And so let's reconsider scattering theory. And so let's think about it like this. So let's start from the beginning, because remember, scattering is really, like I said at the beginning, it's just the theory of eigenstates that have positive energy, right? That's what it is. And so what we have to do then is we have to think about what these eigenstates are doing. And so if I have some weird potential, where this is my, my potential has some weird shape and symmetry, not necessarily a hard ball or something, but just some weird random potential. If I have some weird random potential, then basically what we can do is we can find the eigenstate. We can solve the Schrodinger equation. Then we can find the eigenstate of that potential by solving the Schrodinger equation. H psi equals E psi. And if we can solve the Schrodinger equation, then what happens is we can get the wave function. It might have some weird shape. It's like some weird wavy function. I'm just sort of making it up. If I drew a contour plot of it, it might look like that. And then here it's going to have some weird shape. Right? That's what if I was to like solve the Schrodinger equation for that potential, then this is what it would look like. And so this is psi E of R. This is what it looks like far away, and then as I go closer, it looks more wiggly and weird. But then, so if I had this psi E, then a more general way of thinking about scattering is to say, okay, well, suppose I actually knew what this wave function was for this. Suppose I had actually solved the Schrodinger equation for energy greater than 0. And what that means is that if I put a detector here, let's call this R. And if I put a detector at R, and suppose that my detector has some solid angle, delta omega, for my detector, then how can I figure out the scattering into my detector? Well, how do I think about that? So suppose I have a potential, I solve the Schrodinger equation, and I have a detector. And so now my question to you is, how many particles do I detect? Can I answer that question? How do I answer it? Can you guess? Well, I'll give you a hint. I'll give you a hint. Remember, scattering is all about differential cross-section, right? And when we define differential cross-section, we defined it as 1 over J incident times dr d omega. And what are the units of J incident? Somebody tell me.
It's like probability per area per time.
Exactly. Probability per time per area. That's right. And what is the units of dr?
Probability per time.
Exactly. And the physical interpretation of dr is it's the probability per time going into my detector, because probability is stuff, it flows. And so you should think of the probability as flowing and splashing off of that potential, and some of the probability splashes into the detector. Okay, so what I've done is I've given you a wave function, and this is d sigma d omega. So how do I find d sigma d omega? We have psi e. Then how do we find d sigma d omega? What do I have to do? Can you guess?
Do we get the probability flow or current or whatever?
Yeah, exactly. And how do we do that? Do you remember how to do that?
Yeah, with that equation, there's like a constant. It's like psi east
Exactly.
a star times.
Exactly. That's right. And so it's this guy, psi star del psi minus psi del psi star. That's right. So we get the probability flux. Because the whole point is that once you have the eigenstate, you got the probability flux. And once you got the probability flux, you have everything, because this is just, so this J incident here, the J incident is just by taking, for J incident, you just take the wave function way far away, because the J incident is here. So if I can take if I evaluate J over here, way to the left, then that's going to be my incident flux. And then to figure out what goes into my detector, I just have to figure out the J sub E going into my detector, the J that goes into my detector. And so if I then have, so if I think of my detector as covering some solid angle, but also I can think of my detector as having some area, and there's some vector ds, which is the differential area of my detector. And so suppose that I had this JE in the vicinity of my detector, then dr is equal to what in terms of JE and ds? I have JE, I have ds. JE is the probability flux near my detector, ds is the area of my detector. What is the probability that flows into my detector?
The product of those?
It's a special product. What kind of product? They're both vectors.
Oh, yeah, the dot product.
Yes, exactly. Exactly, because it's a flux. So it's just JE dot ds. And this should look very familiar to you, because this is probability flux. And so this whole product is then probability per time, because it's probability flux is probability per time per area times area is probability per time. So you've seen that before. You know, it's like water flux through a hose. How much water is flowing through the hose? You have to integrate the water flux over the area, cross-sectional area of the hose. So that should look kind of familiar. And so that then means that I can figure so the whole point is that if I have the wave function, then I have everything, because I can calculate the probability flux, and then I can calculate this dr, and I can calculate my J incidence, and then I have I have my differential cross section is d sigma d omega of theta is equal to 1 over the J incident dotted with this guy, which will just, then dr is just going to be the JE at the site of the detector. I'll call that R dot ds. The area of my detector divided by the solid angle of the detector. Okay, so that's going to be basically the point is, then we must find psi. And so that means that it all boils down to the same old thing. In quantum mechanics, it always boils down to the Schrodinger equation. Must solve H psi equals E psi. All right, but the problem is that this is hard to do. So this is hard. And so how do we do it? Let's write it down. So H psi is it's just the same old Schrodinger equation that you've seen before. Negative H bar squared over 2m del squared plus V of R, the potential, times the wave function, psi E of r is equal to E psi of r. Okay, so it's a hard differential. It's hard to solve. And so how are we going to do it? Well, you've done it before, but now we're going to try to do it in a sort of a more general way, because now we're going to focus on this equation, the Schrodinger equation, but we're going to focus on the regime where the energy is greater than 0, and that's the scattering regime. Scattering regime. And we like that, and that's the new regime that we want to understand, because that's the regime where things are moving in space. They're moving from one place to another. Okay, so how do we solve this? So what we're going to do is let's use the Green's function approach. Green's function approach. Now I'm assuming that all of you have seen this somewhere, but I'll just kind of give a lightning review. And maybe you have not seen it. You know, maybe you haven't seen it. I don't know. It depends whether you took a mathematical methods course or not. You know, so I would like to actually know how many of you have seen it. But you know, it's kind of embarrassing. Has anyone seen it? Maybe somebody just shout out if they've seen it before. Green's functions.
Yeah.
Okay, good. Anybody else?
Yeah.
Okay, good. So that makes you feel a little better. All right, but I know that some of you probably haven't. So let's just do a quick lightning review of Green's functions. So this is the idea of the Green's function. So let's say you're given a differential equation. And here we have a differential equation, the Schrodinger equation. And so you're given a differential equation, and the differential equation supposes this. Suppose it's a times the second derivative d squared dx squared plus b times the first derivative d dx plus c of some function is equal to some other function. So let's just say it's actually, let me write it like this. Suppose suppose my solution is this, and then I have this is equal to then some other function, where this is known, but this is, and you know, the A, B, and C are known, but this is unknown. Okay, so, and you've seen this before. This should remind you of like the driven simple harmonic oscillator, for example. Like that could be the driven simple harmonic oscillator. You've seen this before. Okay, so suppose you have this very generic differential equation, then how do you solve it? So one way, so the Green's function approach is to call this part an operator, the differential operator D. And so we can rewrite this equation, and we can say that this equation is the same as saying D acting on my solution is equal to f of x. And so this is a way of thinking about it. And now you can think of this as my solution, because that is the solution, that's what we want. But then you can think of this as the source term. Or you can think of it as the driver, the driving term. The drive term. So, and so the way to think about it is that psi of x is the response of the sort, is the response to f of x. So I have some source term f of x, which is perturbing my system, doing something, and then psi is the response. Psi is telling me how the system responds. So that's like a way of thinking about it. And maybe you've never thought about it that way. If not, then now's the time to start. And here's an example. Famous example, of course, would be Poisson's equation for E and M, that you've all seen it somewhere. Poisson's equation. And here's Poisson's equation. Del squared times phi of r is equal to negative rho of r over epsilon. Okay, where this is the electrostatic potential, and this is charge density. And so when you look at Poisson's equation, basically you're saying that this is the charge density in Poisson's equation, which you've all seen before. You have charge density, and so the idea is that the charge density is equal to this. So when I look at this is the second derivative of the potential. What is the second derivative of the potential? What does that mean? I'll give you a hint. First derivative gives me slope. Second derivative gives me what?
Curvature.
Right. And so basically, a way of thinking about Poisson's equation is that I have some source, I have charge that I arrange somehow, and then the charge causes curvature in the potential. And that's it. I have a source term which then does something to my solution. And for Poisson's equation, what it does is it creates curvature. It's causing curvature in the solution. So wherever I have some charge, I'm going to get curvature because that's the equation. That's Poisson's equation. It just says charge equals curvature. And so it's just telling me how much curvature. So basically we just then have to solve it. We just have to figure out, so what's a function that has exactly the right amount of curvature in space that solves Poisson's equation. So that's, I want you to think about that. So charge density is a source that is doing something to the solution. It's causing curvature in the source, in the solution. Okay, so now let's that's just a way of thinking. And so what we do then is in general, for a differential equation is going to look like this. Some differential operator, which could be curvature or whatever, it's going to be that, I drew it here, it's this one here, right? I gave you the example. And so I have my differential operator acting on my solution is equal to so this is my solution, and this is my derived term or my source term. And I got to solve it. And this is known, typically. Think of this as known, and this is unknown. And so the way to solve it is you look at this and you say, well, this is a hard problem to solve. And what makes it hard is this function. It's hard because of f of x. Because in general, typically if f of x equals 0, then we have a homogeneous differential equation, and then it's easier. D psi of x equals 0 is the homogeneous solution, and that's easier. Homogeneous is easier. But it's this function that's making it hard. So what we do, it's a function f of x that makes it hard. So what we do is we solve an easier equation, and this is the trick. The Green's function trick is that we solve an easier equation first. And the easier equation is, what we do is we say, well, let's take that differential operator and let's suppose that it's acting on the solution. The Green's function is the solution, but now I make the source a really simple source. Do you guys remember what the source is for Green's function?
A delta function.
That's exactly right. So basically what I say is I have a source at x prime, and then what I do is I look for the Green's function is, I think of the Green's function as the response at x due to source and it's a point source due to a point source at x prime. And so this is this is an easier equation. I'm basically saying, what if I put a delta function source at x prime, then what happens to my what happens at the distance x? And so think of it like this. So here's x prime, and then here I have some x. And so then the system responds in some weird way, and that response is the Green's function. The Green's function is just saying, how does my system respond at x due to the source at x prime? And so that's it. And so then you say, and this is an easier problem to solve. So we solve this easier problem, and once we solve it, then we can use that Green's function, because once you solve it, then the trick is that then the full answer, psi of x, is equal to psi naught of x plus the integral of g of x prime f of x prime dx prime. And this is all x. And that's the Green's function trick. So that is the total solution. And it's kind of like magic. It's really cute, and it's very simple to see. So let's just and where this is the homogeneous solution. The homogeneous solution, which is typically pretty easy to get. Okay, so that's the total solution, the general solution to the differential equation. Total solution to the differential equation, which is, remember, d psi of x equals f of x. And so now let's just check that it's a solution. Check. It's really easy. We just plug right in. So let's hit that thing. Let's plug it in. Plug it into d psi equals f and see what happens. See if it works. So let's hit that thing. So d psi of x is equal to d psi naught of x plus d hitting this thing, g of x prime f of x prime dx prime. And then this thing, so what's this equal to? What happened? Yeah, exactly. That's the homogeneous solution. So d psi of x, and now the d is acting, this is an integral over x prime, but the d is acting on the x coordinate, so it can come inside. And so this then becomes the integral of d g of x prime f of x prime dx prime. And what happens when I have d hitting g of x prime? What does that give me?
Delta function.
Exactly. And so this then is the integral of delta function x minus x prime f of x prime dx prime. And what does that equal? By definition of a delta function.
F of x.
Exactly. So that's it. We proved it. It's a solution. D psi of x equals f of x. It solves the differential equation. Okay, so that's the lightning quick review of Green's functions. It's sort of like a little magical trick, a cute little trick, but it's just sort of like recasting your differential equation in a different language. Okay, so now let's apply it to quantum mechanics. Let's apply it to the Schrodinger equation. And when we apply it to the Schrodinger equation, then here's the Schrodinger equation. Negative h bar squared over 2m del squared psi of r plus some potential, my scattering potential, psi of r is equal to the energy times my wave function, psi of r. Okay, so that's the Schrodinger equation. So now let's do a little trick. Let's do a little trick. Let's rearrange it in a funny way. We're gonna pull this guy over here, and we're gonna pull this guy over here. And this is convenient for scattering, because in a scattering problem, what is the source? What is, if I in a scattering problem, what is the thing that's causing something to happen? Can you tell me?
The potential.
Yes, the potential. And so remember, when we have that the Green's function trick, we have like we want to think of the differential operator acting on a solution which is being driven by a source. And this is basically, you think of that as the response of the system to the source. And so in scattering, we want the source to be the potential. And so, but notice when we write the Schrodinger equation, the potential is on the left-hand side. So to do this Green's function way of thinking, we got to get that potential onto the right-hand side. See what I'm saying? It's just a very simple way of thinking about it, because we want that to be the source. So then we got to do it like this. So this is how we write the Schrodinger equation. We're going to, so we're going to multiply by negative 2m over h bar squared and move those guys over. And then we're going to get this. It's going to look like this, del squared psi of r plus 2me over h bar squared. Psi of r is equal to 2m v of r h bar squared psi of r. All right, but now look at this. What is that? What do I call that? Did that look familiar? Do you guys know what that is?
K squared.
Exactly, because k squared is equal to 2me over h bar squared. Exactly, by definition of k. So then what I have, so now I have my Schrodinger equation is del squared plus k squared acting on psi of r is equal to some source term, f of r, where I'll call that my source. But now my source is this. It's going to be 2m v of r times psi of r divided by h bar squared. Okay, so that's my source. So there's the potential causing the scattering to happen. Now, when you guys look at this, though, you should notice that we're sort of cheating. Can you see how I'm cheating? I'm actually sort of cheating when I set it up.
There's a psi in the source, which is weird.
Yes, exactly. So we're kind of cheating because I put my solution in the source. So that's kind of cheating, and that kind of messes things up. But let's not worry about it. So let's not worry about it. So go with the flow. Okay, we're physicists. We don't get caught up in little mathematical details. We just go with the flow. We don't worry about it. Mathematicians worry about that kind of stuff, but we don't, because we're physicists. We just want to get the answer. So we're cheating a little bit, but don't worry about it. Don't worry. Be happy. Right? Like the song. Okay. So what we can do then is we now have this differential equation. So now we have this differential equation that we have to solve. And so this differential equation I can think of then as, some differential operator acting on psi of r is equal to some function. And so to do the Green's function trick, what is the next thing I have to do? To do the Green's function trick, I want to solve it. because this is what we want to solve. That's the Schrodinger equation. Because remember what we're even doing. We want to get that psi so that we can get the differential cross-section. Because once I get the psi, then I get the j, and once I get the j, I get the probability current, and then I can get the differential cross-section. So so to do the Green's function trick, what's the next thing I got to do? Tell me.
Again, the delta function.
Good. I need to do delta, the differential operator acting on the Green's function is equal to what?
A delta function.
Yeah. I basically have to say, if I have, it's basically like saying if I have a delta function scatterer, how does my system respond? How do my particles respond to a delta function scatter? And a delta function scatter typically is pretty easy. That's an easier problem to solve. Because remember, what we're trying to do is we're trying to find the scattering off of any arbitrary potential, and that's hard. But if we can figure out the scattering off a delta function, then we can use that to then generate the solution for the more complex scatterer. That's the whole philosophy of this approach. So now this is the easier problem that we have to solve. Easier. Now we must solve this. And so let's write it down. So here we have it. The Green's function trick is del squared plus k squared, the differential operator, because d is equal to del squared plus k squared, right? And so now we got del squared plus k squared acting on the Green's function is equal to a delta function. And that's basically saying I got a delta function source. What then is the system's response at some faraway distance? And that's the Green's function. So now we got to solve this. Because once we solve, because if we can solve, then we see then that the wave function psi of r is going to be equal to the wave function psi of r is going to be then equal to the psi, and I'll just call it, I'll say it has some, let's just give it some quantum number k. It's equal to then psi k naught at r plus, then I'm going to have the source term, the integral of my source term times my Green's function. And I have to integrate over all possible locations of my source. And here the source term for this scattering problem is this. Here it is, I drew it up here. It's gonna be 2mv psi over h bar squared, so it'll be 2m v of r psi of r 2m, write this well. It's gonna be 2m over h bar squared, v of r prime, psi of r prime. Okay, so that's the solution of the Schrodinger equation, and this, of course, is going to be my solution for this is going to be the homogeneous solution. What is this the solution for? Psi naught of k. That's going to be the solution for what? That's going to be the solution for when. That's the solution when.
The homogeneous?
Yes, and that's the same as when v of r is equal to what? The potential equals
0.
Yeah. And so what is psi naught of k?
A plane wave?
Yes. Exactly. There are many possible plane waves. That's why that's the quantum number. That will be my quantum number. K. That's why I picked this k. because the homogeneous solution sort of tells me which k to pick. So I can say psi of k of r is equal to e to the I k dot r, the homogeneous solution, plus this other part. I'll write it like this, 2m over h bar squared, integral of my potential v of r prime times my my solution, my full solution, times the Green's function. Integrated over all possible locations of the source. Okay, so that is the solution to the Schrodinger equation. That is the general solution to the Schrodinger equation for positive energy. So this is sort of, so you can think of this as a general scattering solution.
Professor, is it really a solution though? Because we don't know what psi is, right?
Yeah, so it is a little bit, we're cheating, but remember what I said, don't worry, be happy.
Okay.
All right? So just follow that advice. But yeah, it's a general solution, but it's, you know, there's something a little bit bogus about it. I guess the way to think about it is like, it doesn't really give us anything. It's not like I really solved it. It's basically, what it really is, it's just a way of rearranging the Schrodinger equation. You see what I'm saying? I just rewrote the Schrodinger equation in this really weird way that you've never seen before. But it's just the Schrodinger equation, okay? And it is, and it's legitimate. I mean, you know, I haven't like done any approximations yet. So this is still, the mathematics is still legitimate. But it's sort of not so, it's in some level you might be thinking to yourself, well, that can't be so helpful, but it is actually. And you know, it will be helpful and it will all work out in the end. And you know how it will work out? Because we will make gross approximations, because that's how it always works out in the end. You know, the physicists, we write down these incredibly difficult equations that we can't solve, and then we make approximations to solve them. And so this is that's where we're going with this. So don't worry, be happy. Okay, so now what do we need? So to go forward, what do we need? What do we need to move forward? What's the next thing we need to make some progress on this problem? Can you guess?
Find the Green's function.
Yes, exactly. So our first step to solve this is we have to find the Green's function. Okay, so let's solve it. So the Green's function is the solution of this equation. I got the differential operator, del squared plus k squared, acting on the Green's function, and that is equal to a delta function. So we got to solve that. So there's a famous solution for it, and this is the solution. I'll just write the solution, because it turns out that solving that is not totally easy. It is not too hard, but it requires like using a complex, using the residue theorem, using complex analysis, and the complex contour integral. And I know that some of you know how to do that, but some of you don't know how to do that. You know, some of you have taken complex analysis and some have not. So I don't want to get all caught up in that, but let's just write what the solution is. It's this, g of r prime. If you solve that equation, it looks like this, negative e to the I k r minus r prime. The solution is quite beautiful. I like writing down the solution because it's a very intuitive solution. R minus r prime. What is that? That's the solution. That is the Green's function. What is that thing? What is that thing physically? I know it's just some weird looking equation, but what is it?
Looks a bit like the Yukawa potential.
Yeah, it kind of does. But also it looks like this. You know, when I give you this thing, e to the I k dot r, what is that? And I say, what is that thing? Tell me, what is that? What is it?
Plane wave.
Yes, moving in what direction?
K.
That's right.
Yeah.
Yeah. And so let's suppose that k is pointing to the right, okay? K is to the right. So this is a plane wave going to the right. Is that correct? Yes. Okay. Now, how is it that you associate motion with that? There is no time when I write that equation. There's no t. How is it that you associate motion with it? How is it that you say it's moving to the right? It's not moving, it's just sitting there. There's no motion. So, and yet there is. It is moving to the right. That's correct. But I'm just pressing you on it for a moment. I'm asking you, why is it moving to the right? How is it that you can think of there being motion to it?
Is it because we can associate k with momentum?
Yeah, but that we do, but still there's no motion here. There's no time. How is it that we can actually say that this thing is moving? How can it move if there's no time? This is not a trick question. It's actually a legit question. Where's the motion in this? Can somebody tell me?
I mean, isn't it just a stationary solution and it moves when you tack on the time evolution factor?
yes, thank you. That's exactly right. Because if this is an energy eigenstate, that only works for energy eigenstates, by the way, then I can say that psi of RT is equal to e to the I k dot r times the time-dependent phase factor that comes with energy, which is e to the negative I e t over h bar. That's exactly right. In which case I have this is equal to e to the I k dot r minus omega t, where omega is equal to e over h bar. And that is a plane wave moving to the right, by definition of plane wave, right? That is a plane wave moving to the right. So that is a wave going right. Okay, so I just want you to remember that when I talk about the motion of some eigenstate, the motion is coming from tacking on this little time-dependent part. And the reason I bring that up is because I remember when I was an undergraduate, it really confused the hell out of me. But so I don't want you to be confused. Okay, so now let's go back to this Green's function. So now I'm asking you, what is this Green's function? So the whole point of this discussion, I just told you that e to the I k dot r is a plane wave moving to the right. And if that's a plane wave moving to the right, then what the heck is that Green's function? Tell me. And I'll draw the source. Here's the source, is a delta function at r equals r prime. What is that function? What is like the physical geometrical interpretation of this Green's function? What the hell is that thing? I start with the source at r prime. What is this weird looking G thing? Tell me. It has a very simple physical interpretation. What is it? Maybe it will be simpler if I put r prime at 0. Let's consider r prime at 0. If r prime equals 0, then what we have is e to the I k r over r. I'm leaving out the 4, well, I guess there's like a -1 over 4 pi. What's e to the I k over r? What's e to the I k r over r?
A decaying plane wave?
Good. It is decaying. That's right. But r, notice that there's no dot product. R here is the radial. It's the radial variable, the radial function. There's no dot product. K is not a vector here. That's what makes it so it's very different from a plane wave. K is not a vector. What is this thing?
So it's like a spherical plane wave or something?
Yes, it is a spherical plane wave. Well, although those are contradictory, it's a spherical wave. Not a spherical plane, you know, it's a spherical wave. And what is that spherical wave going? What direction is it moving?
Radially in?
Ah, good guess. But no, radially out. You had two choices. It's either out. So I want you to go home and sort of figure out, you know.
Oh, it's like radially out, but just like inverted because that negative or something?
Yeah, just think it through. You know, go home and think it through. But this is it. See, it's a radially outgoing wave. So I want you to get that picture in your head. So it's an outgoing spherical wave. Outgoing spherical wave. And it's very geometrical. It's a very beautiful thing, you know, because it's like it's just saying, hey, I have a point source here. It's like, look, I got the pond, all right? The pond is like my probability or my wave function. I throw a rock in the pond, I perturb it with a little pebble, boing. What happens to the pond when I hit it with a pebble? Tell me. You've all done this. What do you get?
You get those rings?
Yeah, those rings have a name. They're called what?
Spherical waves.
Yeah, they're called spherical outgoing waves. That's right. Yeah, or two-dimensional, you know, 2D, 3D, whatever. You know, it's just, you know, it's the outgoing waves. So that's the picture in your mind. You know, throw a pond and throw a pebble in the pond. Boom, you get these waves because you've hit the source with it. You go ping. The delta function is like a ping. You go ping, and then the system goes. It's like, you know, take a bar of steel and you hit it with a little tiny hammer, boom, and you're going to get sound waves emanating from that point. It's the same physics. It's a point source in a wave-like material. If I throw a rock in the pond, it's water waves. If I have a chunk of steel and I hit it with a hammer, it's sound waves. But here in quantum mechanics, it's probability waves, right? Probability waves, or probability amplitude waves to be precise. But I just want you to see it's just all the same kind of phenomena. And in fact, they all solve the same equation. It's just the wave equation. So it's kind of cool. Same physics.
Professor, where did the 1 over r come from, though?
Where did the 1 over r come from? Well, it's some math, and I can very quickly show you the math where it came from. Right now, you know, we can like solve a bunch of equations, but maybe you should think of it sort of physically from just a probability point of view. You know, it's kind of like if I have the particle at some radius, you know, localized at some radius, and the particle is described by this wave function, then at some later time, it has probability to be at a further location, and then a further location, but it's like the probability is conserved. Do you see what I'm saying? And so if I'm talking about the wave function, you know, the probability at further and further locations, that the probability density has to get smaller. That's one simple way of justifying it to yourself. You know, like a light bulb, right? The light bulb is giving off power, and as I get farther from the light bulb, the amount of power goes down. Think of it like that, you know, like to conserve probability. But let's derive it. So, you know, maybe you don't like that, but let's find the Green's function, okay? I'm not going to go through all the math, but it's easy to set it up. So let's find it. And so when we find it, this is how we do it. It's pretty easy. You can do this. You can say, I got to solve this. Del squared plus k squared g of r R prime is equal to delta function. And the trick for solving these Green's function is to go into Fourier space, solve in K space. That's the trick. That's always the trick. It's a big trick. And so you go to K space, and in K space, I would say that G of R prime is equal to the integral of e to the I q dot R minus R prime times some function G of Q d cubed Q. Okay, so that's just a Fourier transform. That's just Fourier space. And in Fourier space, I can also write my delta function. Delta of R minus R prime is equal to the integral of e to the I q dot R minus R prime d q q. Okay, so that in Fourier space, then I can write my Green's function and my my delta function in Fourier space as integrals over waves. So that's okay, just from the common knowledge of Fourier transforms. So now plug these guys in, and so then you get this. You get del squared plus k squared acting on this integral e to the I q dot R minus R prime times G of Q d cubed Q is equal to the integral of e to the I q dot R minus R prime d cubed Q. And then I bring this in. And so when I bring it in, what does the del turn into? I bring it into the integral. What does the del squared turn into? This is the whole beauty of it.
Minus IQ squared.
Exactly, which is going to become minus Q squared, right?
Minus Q squared, sorry.
Right, minus Q squared plus K squared times e to the I q dot R minus R prime G of Q d cubed Q is equal to integral e to the I q dot R minus R prime, I'll say times 1 d cubed Q. And so now look, on the right hand side, I just have I got this wavy thing multiplied by the number 1. But on the left hand side, I got this wavy thing multiplied by this times this. So then I can say that that minus Q squared plus K squared times G of Q equals what? Look at that equation and tell me what it equals.
1.
Yes, exactly. And so then G of Q is equal to 1 over K squared minus Q squared. Boom. So simple. So finding the Green's function in reciprocal space is trivial, totally trivial. But then I still got to find it in real space. So now I got to find G of R minus R prime is equal to now the integral of e to the I q dot R minus R prime times G of Q, which is 1 over K squared minus Q squared d cubed Q. Okay, so now that's how you find the Green's function. You got to do this integral. So that's how you set it up. But it turns out that this this integral is not super hard, but it's kind of tricky. Okay. And so I'm not gonna work it out in detail. So you can look in the book. And there are various books that work it out. often that you have to do a contour integral to do it. But if you solve that integral, you get the Green's function, okay? So, but I wanted to set it up for you. I just wanted you guys to have a sense of, you know, where it all comes from. But when you do it all, then you're going to find that this is what you're going to get, all right? When you dot all the i's and cross all the t's, you're going to get that the Green's function is negative e to the I, k, r minus r prime, all over 4 pi r minus r prime, outgoing spherical wave. All right, so there you have it. And so now what we're going to do then is we can write down the solution to the Schrodinger equation. So the solution to the Schrodinger's equation is this. Psi of k of r is equal to a plane wave plus 2m over h bar squared times the integral of v of r prime psi k of r prime times the Green's function and the Green's function is going to be this thing. It's going to be oh shoot, this is going to be negative m over 2 pi h bar squared v of r psi of r times this outgoing plane wave part, r minus r prime all over r minus r prime integrated over r prime. Okay, so that is then the solution to the Schrodinger equation. And all right, so now we still want to see if we can get that to be something that's a little bit more manageable. And so what we do is we do a trick. What we do is we do a trick. We assume that the v of r is small, and it usually is. Like if I'm scattering off of a proton, then the proton is pretty tiny, and so we say that the potential in this integral is the size of this integral is set by v of r prime, and we say that that's small. But but our detector is far away, big, and so r prime is small, but r is big. So because our detector is typically very far away, detector. And so in this integral, notice that in that integral we have both r and r prime coexisting in the integral, but now we're going to start making approximations. So our approximation is that r is way bigger than r prime, and that's typically a pretty good approximation. And so in this approximation, when r is way bigger than r prime, then what happens is we can say that if I have a function r minus r prime, then I can say that this is equal to approximately equal to f of r minus r prime dot gradient of f of r. And you guys have seen that before. It's just calculus, right? It's like saying f of x minus delta x is equal to f of x minus delta x d dx f of x. So you guys have all seen this before. So it's just like that. And so now let's do this, but now let's plug it in, because now using this trick, then we can write that e to the I k r minus r prime over r minus r prime is equal to e to the I is approximately equal to, for this approximation where r is way bigger than r prime, e to the I kr over r minus r prime dot del e to the I kr over r. And then with a little bit of algebra that I don't have time to show right now, then we can show that this is approximately equal to e to the I kr over r times e to the minus I k r hat dot r prime. All right, and that just took a little bit of algebra, but so basically I can replace this thing with this thing. And that's a very significant thing because now let's plug it in. Let's plug it into here. And so now we see that our wave function, and I'm almost done, guys. Just want to get, because I just want to get to this penultimate result in just 1 minute. So now we see that our wave function that we derive is equal to a plane wave, e to the I k dot r minus, I'm just plugging it all in, m over 2 pi h bar squared integral of e to the negative I k r hat dot r prime v of r prime times psi of r prime d cubed r prime, and I pull, and this part I can pull out of the integral, pull out of integral, because it doesn't depend on the r prime anymore. Okay, and so then this is outside of the integral, e to the I k r over r. And so what that means is that my wave function, my most general scattering wave function, has this form. It's a plane wave plus this other part, this f of r hat times e to the I k r over r, where this mess of stuff is a function of r hat. See, the only unknown, once you do the integral, the only unknown, the only variable that remains is r hat. Because remember that the definition of r hat is that r is equal to r hat, and we have this. Remember, because we have this r is where the detector is, and r prime is integrating over the potential. Just so you can remember all of the geometry. And so this is a really big deal because now f of r hat is equal to this thing, negative m over 2 pi h bar squared integral e to the negative I k r hat dot r prime v of r prime times psi of r prime d cubed r prime. And so this is our big result. And so that's what we'll talk about more next time. So I just want you to see that what we have is a plane wave plus an outgoing spherical wave. In other words, our wave function, our scattering wave function looks like this. Here's our potential. We shoot a plane wave at it, and our wave function looks like this. You can draw it very easily. It's a incident plane wave plus an outgoing spherical wave. Okay, guys, sorry for going over. I just wanted to finish that. So we'll talk more about this next time. Bye-bye.